My name is Miles Owner, and for my presentation, I chose the paper Liberating Libraries Through Automated Fuzz Driver Generation, Striking a Balance Without Consumer Code. This is a paper that came out of EPFL Switzerland with the authors Flavio Toffolini, Nicholas Badeau, Zerab Tsanadze, and Matthias Peyer. This paper tries to look at generating fuzz drivers to fuzz libraries without needing experts to write the fuzz drivers or needing examples of consumer code in order to automate the generation of these fuzz drivers. So first, what are software libraries? Software libraries are collections of commonly used code that can be used between different executables. They can be either statically linked or dynamically linked. Statically linked binaries are built into the executable or application, whatever it's being used for, at compile time. That means that whenever that executable is ran, that library is baked into the memory and baked into the program. In this case, if two different executables are using the same library, they each have their own copy of the library that they're working with. This can mean that if two different executables need different versions of a library, they can use them separately. However, if, for example, there's a vulnerability in the library that needs to be patched, for that to be patched for all executables that use that library, they would have to be recompiled. And also, within memory, this can cause extra memory usage, because since every single executable has their own version of the library, there's lots of duplicates in memory. But however, it also makes libraries executables more portable with static linking, because there's less outward dependencies for the system. We can contrast this with dynamically linked libraries, which are injected into the memory space of an executable at runtime. This lets it so that executables can share one library between themselves. This solves a problem where if a library has if multiple executables in a library, it uses less memory on the system. And also, for example, if there's a vulnerability in a library, that can be easily patched for a system by just updating the library that's being shared between all the executables. These are .so files in Linux, which stands for shared object, or DLLs on Windows, which stands for dynamically linked library. Some examples of libraries include glibc, which is GNU's implementation of libc, which implements various different commonly used C functions. Musil, which is also another version of libc, just not made by GNU. OpenSSL, this is a open source implementation of various different cryptographic functions that are used. This is one of the largest libraries used in the world, because you're probably using it right now watching this video. If you're streaming over HTTPS, because HTTPS uses a lot of functions that are implemented in OpenSSL. Log4j is another example of library. It's a JavaScript library that implements logging. And also libwebp, which if you ever use a WebP file, you've probably interacted with. WebP is an image format, and libwebp is various different ways of interacting with it. Now, why is fuzzing libraries important? Libraries can also contain bugs, just like any other program. If an executable uses a library that is vulnerable, the executable itself opens itself up to vulnerabilities, depending on how that library is used within the executable. Some famous examples of library vulnerabilities include Heartbleed, which was an OpenSSL. This caused an issue where an input from the OpenSSL library trusted an input that could be taken in from the user, and once taken in, would read beyond the bounds of the array that is allocated for a certain region of memory, therefore allowing the attacker or whoever is reading the memory, that shouldn't be reading the memory, to read arbitrary sections of memory, which could contain secrets or other things that they should not be able to read. Another example is log4shell for log4j. This vulnerability allowed servers and services that use the log4j library to be vulnerable to remote code execution, allowing attackers to execute arbitrary code on a service, which caused a lot of issues, as arbitrary code execution is very powerful and can allow an attacker to take over a server. libwebp also had its own CVE. I think it's had multiple, but one right here, for example, is CVE 2023-4863, which let an attacker execute arbitrary code through a function that would just render images. And so this let people who were using libwebp applications vulnerable to zero-click remote code execution attacks, where if they just rendered an image, they could execute arbitrary code. An attacker could execute arbitrary code on the victim's machine. And I think this was used in some examples of spyware it was used as an attack vector for some types of spyware, I think NSO group spyware. But this brings a question: how can we fuzz a library? Libraries by themselves can't take in inputs. An executable, which has a main function and also supports input and output, is able to take in test cases and do something with them. Most fuzzing frameworks, such as AFL or AFL++, are designed around executables. Libraries, however, are meant to be used within the context of an executable. By themselves, they cannot take in a test case and do something with that, which is how, as I said previously, fuzzing frameworks were designed. Fuzz drivers are intended to help fill this role in for a library. A fuzz driver is basically an executable which is designed to be fuzzed that calls a library's functionality. It's basically a wrapper around a library that gives it an executable like behavior. With this, we're able to feed it into a fuzzing framework and mutate inputs, fuzz them, check for coverage, and see where a library might have some type of vulnerabilities or bugs in them. A lot of effort and thought has to be put into writing fuzz drivers. It's not that you can simply just call a bunch of functions randomly and expect it to give you meaningful fuzzing behavior. For example, a lot of libraries, there's a lot of setup that's involved when using certain functions. Here's an example from OpenSSL. EVP is a front-end is an interface to work with certain ciphers, for example, AES. And here we have EVP encrypt in it. What this does is that it sets up some environmental settings in order for their functions of this crypto system to be called. And so therefore, it's necessary to call this before you call other functions that have this as a dependency. And so if you don't do this in a fuzzing driver, then you're going to have a behavior in a fuzz driver that does not represent how the library will function in the real world. Drivers are very useful in fuzzing libraries. They also have a lot of cost behind them, especially in terms of resources. For example, they're very time intensive to write. Fuzzing drivers written by humans requires a lot of effort put behind them, and also requires a lot of expert knowledge of the library that's being used. As we said previously, of course, you have dependencies, and that can lead to very complex chains of functions that have to be called in order to set up the environment, and different environments have to be used as well to test different parts of the library's functionality. The library also has to, of course, the fuzz driver has to have enough diversity in it in order to fully explore a library's coverage. Otherwise, badly written fuzz drivers can lead to a plateau in coverage and not be able to fully explore binary and find bugs and vulnerabilities that might be present. So the extended difficulty of not only you have to fuzz the input space of the binary, but you also have to try different combinations of the API. So that greatly increases your problem set. And also, in cases where you have a a limited time that you have set aside to fuzz the library, there's a trade-off between making the fuzz driver and fuzzing it. The more time you spend making the fuzz driver, the less time you might have to be able to fuzz it. And the more time you spend fuzzing it, the less time you might have to make a fuzz driver. And there's pros and cons to each one. And it's important to be able to find a sweet spot that helps increase and promote diversity and fuzzing and increase your coverage of the library. Brings up the question, how can we make fuzz driver development easier? Fuzz driver development. So there are currently two types of automated fuzz driver development. They can be put into two categories. The first one is consumer dependent. What this means is that the automated fuzz driver development is based on how current programs in the wild, ones that are being used, or programs that are written that use this library, they look at those programs and try and mirror and mimic their use of the library. Of course, there's also consumer agnostic um, uh, fuzz driver development, which does not depend on existing library usage and tries to figure out and determine how to use these libraries in a way that doesn't require currently existing programs. Some previous work that has been done in automated fuzz driver development. In the consumer dependent side, you have FuzzGen, which tries to infer the API call dependency graph for programs that use the library in the past. So what this means is that FuzzGen looks at what these programs are doing and tries to identify, okay, this function should be called before this function, and these different outputs or inputs to the functions should then be also used for this next function. And that way, it can try and make a meaningful fuzz driver that will give out drivers that can find meaningful bugs in the library. RomFuzz focuses on using LLMs to write fuzzing drivers, and that way the LLMs write these fuzzing drivers, and then they can be tested by a traditional fuzzing framework like AFL++. And this tries to also address issues in previous works that have used LLMs. OSS FuzzGen is a tool actually made by Google. Google operates the OSS Fuzz project, which tries to fuzz open source software through automated fuzzing. Projects that are sufficiently large enough and critical can request Google, can integrate into their, I think, CI/CD pipeline. Google's OSS Fuzz, which will then gradually fuzz these projects over time and try and identify vulnerabilities that way. On the consumer agnostic side, we have a Hopper. What this does is it treats library testing as grammar fuzzing, as interpretive grammar fuzzing, and makes fuzz drivers that way. And GraphFuzz, which tries to build lifetime aware data flow graphs in order to generate valid API sequences to implement in fuzzing drivers. This brings us to the tool that's used in this paper, or introduced by this paper, Liberator. Liberator tries to address challenges that previously exist in writing consumer agnostic automated fuzz drivers. identifies trade-offs between like the time that it takes to generate a fuzzing driver and the time it takes to test it. And of course, this came from EPFL in Switzerland. Generating versus testing. As stated previously, the more time you spend fuzzing, the less time generating fuzzers or fuzz drivers, the less time you spend fuzzing. And we have a graph here that shows how Liberator is able to operate on a variable basis and spend more time generating tests, fuzz drivers, or less time generating the fuzzers and more time testing. You have examples where a manually written fuzzer takes no time to automate, no automated time to generate the drivers because they're written by humans. But of course, there's human cost to that, and so tries to identify trade-offs. So there are three main challenges that Liberator identifies. C1, or challenge 1, is predicting complex API combinations. So there are many different ways that API can interact with itself in a library, especially a sufficiently large library. And being able to know how this API can interact with itself in a valid way is important. Challenge 2 is avoiding coverage wall bias. And so Liberator, the people behind Liberator identified that previous works on automated fuzz driver development seem to discard possible fuzz drivers candidates once they hit a certain coverage wall. But people on Liberator thought that these walls, given enough time, could be broken through and lead to better improvements. And also challenge 3, which is deep testing of diverse API chains. So given how many API different fuzz drivers are made, it would be impossible to deeply and meaningfully test them all. How does Liberator address these concerns? First, Liberator generates an API flow graph that tries to build a graph of different dependencies within the library. Within this graph, every single node is an API function. And every single directed edge is a dependency of the function. Liberator does this through many different ways. First of all, it uses different variable length relationships, such as buffer size, to try and determine where this buffer should go, and if one function that takes in a buffer, another function that writes to a buffer, if there's dependency between the two. It also looks at allocations. So Liberator assumes that allocations tend to be earlier in the API flow, and that deal allocations of those structures are later within the API's flow. It also looks at lifecycle objects to try and determine dependencies. And this tries to tackle challenge 1, identified by Liberator, which is predicting complex API combinations within fuzzing drivers or fuzz drivers. Liberator also tries to generate these drivers from the API flow graph by picking a source function that doesn't have any dependencies and trying to append those dependencies to it and respecting the arguments that it takes. But also, not all these drivers can be good. So what Liberator does is that for about 5 minutes, it will fuzz the driver to try and determine if it's good or not. Where Liberator differs from previous works is that instead of using coverage as a metric for if this driver is good or not, it checks the seeds. And so if a driver produced by the previous step produces new seeds that are interesting, it keeps the driver. And if it doesn't produce any new seeds, it discards that and determines that it's bad. It does this to try and tackle challenge 2, which is avoiding coverage wall bias, where if we just looked at new coverage generated by a driver, it could lead to incorrect results. Also, once we have our drivers that we determine are good and interesting, they are clustered. How Liberator does this is that it converts all the API chains into strings with the function names to represent the different chains. And using these chains, it calculates the Levenshtein distance between all of them. This is a representation of how many different substitutions you have to make in a string or edits to a string in order to go between the two, and uses to cluster them. And so from these clusters, Liberator then picks a random representative to represent that cluster. And this does this in order to pick more diverse drivers, because if we used every single driver that came out from the generation, we would have a lot of overlap. There'd be a lot of overlap. And this tries to tackle challenge 3, which is trying to do a deep test of diverse API chains. Because if we pick multiple different drivers from a similar cluster, take cluster 1 for example here, if we pick 2 drivers from that, then there'd be a lot of overlap and we'd be wasting computational resources. Next, we'll look at some of the experimental results that came out of Liberator's testing. So looking at the coverage that was generated by Liberator over time, we can see here we have 4 different columns for Liberator and only 1 column for coverage for Hopper and OSS Fuzz. Here, the 4 different columns represent the different combinations of the time it takes to generate the fuzzers and the time it takes to test them. So in the case where testing is 0 hours, it uses just the coverage that comes out of the sentences, the pruning and the shallow testing of the different fuzzers. And you can see here for majority of the cases, Liberator has a greater greater coverage over the libraries that's testing for Hopper, and for OSS Fuzz for half of them it has positive coverage improvement. And OSS Fuzz is the drivers that are generated for OSS Fuzz, and Hopper is that automated tool. And here we have the list of the different bugs that were found by Liberator during its testing, as well as false positives. So you can see on the left here, most of the bugs are centered on 3 different libraries: the CJSON library, libtiff, and libucl, where most of them have been fixed, as well as the PR numbers for their respective repos. So it came out with 24 different bugs that were found through its testing. Of course, there's also false positives that we have on right here. And so this, since this is automated, there are going to be issues with some of the drivers that are testing. So when these drivers are being tested, they're going to have API chains that are not wholly valid. So you might have a crashing input for one of the fuzzing drivers, but that doesn't really represent actual vulnerability with the library that's being tested.